Hey there, glad to be back. This is Verbsky. We're in chapter 6 doing section 6A. 6A, I think you're going to love. It's mean. Hey, let's get right after. That's average. Median and mode. Surprisingly, even though they're simple, there's quite a bit of power derived from mean, median, and mode. We're studying data now, and I think you're going to really like it. Let me just make up a good set of numbers. Let me pause for a second. I'm going to find my calculator. Hey, I'm back. Wow, I almost messed up. I'm recording now. So what we're going to do is create a set of data of like 1, 2, 3, 3, 6, 7, 7, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 13. Now, there's 10 items in my data set. And let's start with the easiest, mode. Mode is the number that occurs most often, and clearly it's 7. 3 was a close second. Can you have two modes? The answer is yes. If there happened to be another 3, the modes would be 3 and 7. The median is the middle number, or the average of the two middle numbers, because this set is a set of 5 and a set of 5. Technically, there's two middle numbers. One way to do this is say, what's the middle of 6 and 7? Well, 6.5. I'm done. Else, you go 6 plus 7, take the average divided by 2, you get 13 halves, which is 6.5. The most strenuous piece is average. Oops, mean. We don't say the word average anymore. And you got to add them all up. 1 plus 2 plus dot 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 plus 13 divided by 10. And we get 3, 9, 15, and 21, 36, 46, 45, 55, 58 divided by 10, which is 5.8. There's a variety of ways to do this. You could have done that old-fashioned way, but let me get all fancy here. If you hit the stat key on a TIE 384, so if you don't have one of these, well, this is kind of, fast forward, edit, and I could enter 1, 2, 3, 3, 6, 7, 7, 7, 9, 13, and you go, I want out. Second, quit. Then if you hit the stat key again, and you go over to calculation, first variable statistics, this is fancy. I'm looking at list 1, frequency, nothing, calculate. If you have the older version, you just hit enter. Then you can see X bar is the average. Hey, let's start calling that X bar right now. Oops, I said average. I apologize. It's mean. Summation of X means add up all the things. So they did that for you. It's 58. Summation of the squareds means you go 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 3 squared, which is 9, 6 squared is 36, and they add them all up. These are standard deviations, which we'll be talking about in the next few sections. The minimum value is 1. We'll be doing quartiles. There you go. The median is 6.5, the 50% mark, the 2/4 mark, quarter 3, the max at 13. So it's best to do it by hand if you can, but your calculator does do all this automatically for you. Obviously, you can see it didn't calculate the mode. You got to do that on your own. Next page. Now, sometimes you get these things called outliers. It's like when you got test averages like 55, it was a really hard test, 61, 68, 71, 73, and then somebody gets the 100. Do you think that's an outlier? What is an outlier, and how do we find one? Well, we're going to have to learn procedures to define whether something is an outlier. And, you know, this book is pretty awesome. I like it. And they have this thing that talks about what an outlier is. And I guess I can write down their definition. An outlier is a data set in a data set is a data value, like 100, that has a much higher or much lower than almost all the other values. So this one's much higher. An outlier can change the mean of the data, but generally does not affect the median mode. Oh, okay. Hold it, my dog. Let me hit. Hi, I'm back. My dog was freaking. He wanted to be fed. It's like an hour before normal. But anyway, what I'm going to do is of this set, I'm going to find the mode. Oh my, there's not one number the same. So we go, there is no mode. You have to have at least two of something to have a mode. The median is the middle number. Set of three, got to take the average. I can split that, I think. They're 3 apart, so half is 1.5. So I think it's 69.5. But if you're not like that, just go 68 plus 71 divided by 2 on your calculator, and you'll get 69.5. Now, the mean, i.e. x bar, is on 55 plus 61 plus 68 plus 71 plus 73 plus 100, enter, divided by 6. 71.3 repeating. Now let's cross it off and switch to red. The mode is still no mode. A good teacher probably would have made like 271s or something. The median is now just the middle number. You got a 2 and you got a 2. There's officially a middle number, which is 68. This did change by a little bit. But the mean, now this calculator is really cool because you can go back up and you can select, and then you can just go delete, 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 delete. Most of you will have to add up the numbers, but now divide by 5. And now the mean is 65.6. So the mean dropped more than the median. Is that enough? The answer is we don't know yet. We need to determine a method to determine if 100 is an outlier. But unfortunately, we're not going to learn it this section. So once again, an outlier can change the mean of the data set, but generally does not affect the median or the mode. In my example, the median was affected just a little bit, and the mean was affected more. Therefore, 100 is a potential outlier, but we have no systematic process yet for determining outliers. And don't you worry, we'll give you 2. Yeah. Now, once again, without getting crazy, there's a good reading, there's a problem called average confusion. I cannot do as well as the textbook. I cannot outperform MML. Like, hey, go get some extra help and work on this. It's impossible. You know, they're a textbook company. But there's all these great problems, and I will try my best. Now, one thing we will be working on is shape of distribution of data. And you may recall, you may have heard, you know, people talking about the standardized bell-shaped curve, histogram, bar graphs, all this type of thing. But what you're going to do, and what I do, is when I do this, I just put dots in the center, and I just try to connect them. And they're going to have all sorts of different names and actual names for this. This is going to be called a normal distribution. Now, nobody that's taken a test wants a normal distribution. That means I have to give so many F's and so many A's, and the major grade's a C. And nobody wants the standard normal bell-shaped curve for your grading scale. For my grading scale, I guess you guys would like to see something like, boo! Ah, that's good. You'd love that. Do I have a name for that one? Nope. But then that would be really awesome. Only maybe one F, whole bunch of, maybe a couple D's, some C's, whole bunch of A's and B's. But lovely. There's the ones that look like camels' backs. They just come off, woo, whoa. They might want to call this like bimodal. And once again, that's if somebody made a histogram of the data and you're driving a curve through the centers of the tops of the histogram. The book gets into modes and talks about how many modes there are. Like this and this and this are the modes, and this would be a mode, and this would be a mode. You have to understand that this book is quite different than most text. It's kind of new terminology for me, but that doesn't mean it's not any good. Now, just so you know, we are going to be studying mostly the normal distribution because it's good for like ACT data, SAT data, things like that. But in real life, there's a lot of flexibility with this normal distribution. So we're going to do a lot of cool stuff with that one. But there's nothing saying we can't do cool stuff with the one we invented or cool stuff with something called a bimodal. What I want to do is work on the traditional stuff, and I only plan on asking traditional questions in MML. What I want you to do is, of course, you're going to be assigned to do the reading. That's an honor system assignment again. Now, traditional distributions that you need to know the lingo for this is known as left skew. Left skew means data on the right. So basically a whole bunch of high test scores and somebody down here and there's somebody right there, like one student got a 10% and one student got a 15%, and then Most of the people in the class did remarkably well. So all the data is over on the right, but we say it's skewed to the left. This is left skew. I always get it mixed up, but I know it's opposite of what I think. So right skew, ton of data on the right, ton of data on the left. So it's skewed, pulled. So this is right skew. They skewed it. But data on the left. And then symmetric, it's not a skew, it's just symmetric. Bell-shaped curve, data that we most likely will be working with. And that's, they, once again, talk more about it in the reading, that there's not anything I really need to do with respect to that. Now, if you take a full class in statistics, you will learn to work with left skew and right skew. And sometimes you can actually push left skew and right skew into almost into a symmetric data, but I shouldn't even say that. Kind of a symmetric world, and still do approximation based on the left skew and right skew data, but you transferred it into a symmetric world. Statistics crazy, but you can do this really cool stuff. Next, and we'll work a lot on this, but not in this section. Next, we got data with low variation. Maybe like one or two high values, one or two low values right in there. Maybe one or two high values in there. But all the data is nice and tight. It's like you got a 10%, 28%, a 61, a 70, a 72, 74, 76, 77, 91, 100. All the data stacked in the middle, nice and tight, with only maybe a little bit of variability on the outside, and maybe not even that. Maybe these weren't even there. And this is nice and tight. It has low variability. But don't worry, we'll have a way to measure variability. So you don't necessarily need to understand right now, even though I think it makes sense, but we are going to measure variability. Now, high variability. Data's all over the place. Whoa. Nice big spread of data. Data's like a mile apart. You know, like you got 1, 13, 17, 50, 72, 100. Lots of space, a lot of variation, a lot of, what I like to think, if we found the average, so let's say the average is somewhere in here, the mean, then these guys are a really long ways away from the mean. Therefore, we say it has high variability. Now, if I would do the dumb one in the book that says moderate variation, well, it's really hard to draw. It's really hard to explain, so I'm not going to do it. Variation describes how widely data values are spread out from the center of the data set. Very cool. Sorry, guys. This is the end of the lecture. What's important? Mean, median, and mode. You know what? I want to end with... No, I think you got it. No, I changed my mind. If you have a 1, 1, 2, 3, 3, 7, 9, 9, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. There's 2 1s, there's 2 3s, there's 2 9s. The mode is 1, 3, or 9. The median is you got a set of 5, you got a set of 5. The median is 7. The mean, don't care about 1 plus ... plus 13, divide by 11, whatever, you can do it. I just wanted to get one more example of mode and median in before we quit. On the homework, it's going to be short and sweet. You're going to be doing a lot of mean, median, and mode. I'm going to do a reading assignment on your honor, and of course that counts as another, like, as you, if you don't do it, you don't do it. I'm not going to know. But I'm not a big believer in like doing something I don't believe in, I guess. So if I'm telling you to read 6A, I truly believe 6A is important. So read it on your honor, you score a point. If you don't read it, well, you score a point anyway, but you're not doing it, not very honorable, I guess, but it's some good material. So I'm going to make an MML assignment, and that's it. Shortest lecture of the semester.